Hello, and welcome to this week's lecture at the Yorkshire Natural History Museum. I'm Oliver Weeks, paleontologist and curator at the museum. Now this week is a little different. The live recording had a little bit of a hiccup, so I'm re-recording this after the fact. So, death of dinosaurs, otherwise known as the Cretaceous-Paleogene, or KPG, mass extinction, previously referred to as the Cretaceous-Tertiary mass extinction, or the KT mass extinction. So this talk will cover the concepts of mass extinction, how we know it was caused by a meteorite, how we know how big that meteorite was, the effects of it, and how we know that it happened in June. So you've probably seen these images of meteorites hitting the Earth, like this, dinosaurs startled, going about their day-to-day, T-Rexes looking on wistfully. But how do we know this? Where do we get this idea of a meteorite slamming into the Earth? So, since the initial discovery of dinosaurs, it has been obvious that they're no longer with us. We don't find velociraptors rummaging about in our dustbins, brachiosaurs trimming the tops of trees in our local park, or a Spinosaurus chilling in the River Don. The question of where they went is as old as their discovery itself, and this prompts the idea of extinction. So here are some old ideas about how the dinosaurs went extinct. Some of them are quite reasonable. So potentially competition with mammals. This was a time where mammals were starting to diversify. Most of them were quite small during most of the Mesozoic, but it's possible that there was the beginning of competition with mammals. Spread of poisonous plants. Of course, angiosperms had just evolved in the Cretaceous, so plausible. Mutations from cosmic rays. Random epidemics, increased seasonality, maybe making habitats less stable. Extensive volcanism. Of course, that's the cause of other extinctions as well. Over-specialization is probably something that would work with other things going on as well, if the ecosystems were less stable. And then we have some other slightly stranger ideas, such as hormonal imbalances, where they grow excessive horns, slit vertebral discs, cataract blindness, a bit strange, hay fever, paleoveltschmerz, so born with the ancient world. Don't know how that would cause an extinction, but it was proposed. And dwindling brain and consequent stupidity, but also another strange one. This is so for more of the proposed previous hypotheses of the mass extinction, recommend Dinosaurs Rediscovered. This is a paraphrase list that was featured in that book. So how do we get to a massive space rock? Let's rewind a little bit and give a bit of context. So we need to understand the mindset of geologists at the time. Before the late 1700s, the interpretation of the geological record had been biblical. The strata having been either created as they are or laid down in the Noachian flood. And this is where the idea of catastrophism comes from. Some catastrophic event causing the buildup of geological layers. However, on closer inspection, the geological record became apparent that the geology of the Earth held a record of processes which still occur today, stretching all the way back in time. This first quote here is from James Hutton in 1788, he says, "No vestige of a beginning, no prospect of an end." This summarizes this stretching back of time that we see and the record of Earth processes. It demonstrates the picture in the background might also be familiar. That's the Hutton's unconformity. It demonstrates the vast amounts of time in the geological record. The vertical beds that you see in the bottom needed to be deposited and then deformed to that extreme degree. And then a lot of erosion had to occur, and then another depositional event, and another episode of deformation, and another episode of erosion. So the concept of uniformitarianism naturally follows from this. The present is the key to the past, a concept developed by Charles Lyell in his Principles of Geology. Uniformitarianism, that the geological record can be explained by modern geographical processes, formed a natural counter to the idea of catastrophism. Thus there was pushback to any idea that seemed to contradict uniformitarianism. So, were the dinosaurs killed off by a gradual process? Mass extinction has been a staple idea in modern paleontology, but the concept is barely 40 years old. In 1982, these two guys, Raup and Sepkoski, plotted the number of marine families through time and found 5 times in Earth's history when the taxonomic diversity decreased dramatically. At the end of the Ordovician, Devonian, Permian, Triassic, and of course the Cretaceous. At the end of the Cretaceous, 11% of marine families died out. Over 75% of all species. It's the most famous of the mass extinctions, but it's actually only the third worst mass extinction. So this concept remained controversial for many years, partially because it did go against this idea of uniformitarianism. We don't see these massive decreases in diversity today. Well, so where do we actually get this idea of a meteorite from? In 1980, Lewis and Walter Alvarez were formulating a way to objectively measure the rate of sediment accumulation to create a yardstick of time. Their idea was that iridium, a transitional metal rarely found on Earth but abundant in space, rains down constantly through mini meteorites. If there is more iridium in a sediment layer, there has been more time for these mini meteorites to build up, and the layer will have been deposited more slowly. However, when looking at the KPG boundary in locations in Denmark, Italy, New Zealand, there's a massive increase in iridium. So did the sedimentation rate just slow down by several orders of magnitude, or was something else at play? They developed a hypothesis along with Frank Azara and Helen Michael as follows. A hypothesis is suggested which accounts for extinctions and the iridium observations. Impact of a large Earth-crossing asteroid would eject about 60 times the object's mass into the atmosphere as pulverized rock. A fraction of this dust would stay in the stratosphere for several years and be distributed worldwide. The resulting darkness would suppress photosynthesis, and the expected biological consequences matched quite closely the extinctions observed in the fossil record. So, it's a pretty solid hypothesis. How big did they predict that the meteorite would be? So, they ran the numbers, and using the equation where F is the fractional abundance of iridium in meteorites, S is surface area of iridium just after the impact, A is the area of the Earth, 0.22 is the proportion of the material from Krakatoa eruption that entered the stratosphere. They found that the rock would have weighed about 34 billion tons. and would have been 7 kilometers wide. And that would result in a crater 150 kilometers in diameter. So keep that number in mind, 150 kilometers. So it was further hypothesized that it would have caused wildfires in the local area, perhaps across the globe, through superheating of the atmosphere. Soot and debris thrown into the atmosphere would then block out the sun, leading to a global temperature drop of about 7 degrees for several decades, halting photosynthesis and causing complete ecosystem collapse. And then a long-term temperature rise would result from the increased CO2 from the melted rock and forest fires. But what other evidence do we have of the mass extinction? So around the Gulf of Mexico, there are several deposits of strangely perturbed rock, limestones that seem to have been ripped up and dumped. These could be explained by a meteorite impact in the ocean nearby. So now we have the general location, and the boundary layer of the KPG seems to get thinner the further you go away from the Gulf of Mexico. The lower layers of the Caribbean deposits are also filled with glassy spherules. These are interpreted as vaporized rock thrown up into the atmosphere and formed into tiny spheres as they tumble back to Earth. But unlike volcanic spherules that typically have the chemical composition of basalts, these have the composition of limestones and rock salt. The layer of ripped up beds cover these layers of spherules, and then on top of that is the layer of iridium that had been found. There's also a spike in fern-spore abundance immediately after the extinction in North America, indicative of them being wiping out of tree cover and recovery of fast-growing plants. Okay, so we have this circumstantial evidence, but where is the smoking gun? Well, the crater had actually already been discovered by accident during an oil drilling expedition where they found melted rocks where they'd expected oil. That expedition was abandoned, but the evidence was recognized by geologist Alan Hildebrandt, who as the proposed impact site. When the rocks were tested, they dated to the exact age of the KPG boundary, and geophysical surveys have shown that the crater has an inner ring of about 80 kilometers and an outer ring of 130 kilometers, which closely matches the estimate of the original hypothesis. So the culprit has been found. But was there another reason for mass extinction? Yes, you guessed it. Hay fever. No, just kidding. It's extensive volcanism. So at the time, the area, which is today India, was very much on fire. There were lava flows up to 2 kilometers thick, covering an area of up to 500,000 square kilometers. And this all began around 66.25 million years ago, around 250 years before the mass extinction. The ash and sulfurous gases in the atmosphere would have caused global cooling of perhaps 2 degrees, which could have contributed to the instability of these ecosystems leading up to the impact of the meteorite. There we go, that's the map of India with the Deccan traps. So were they already on the way out? Some studies have suggested that dinosaurs were in a long-term decline. They show in all 3 major lineages, the theropods, sauropods, and ornithischians, there's a decline, but with some groups within them still going strong, such as the ceratopsians and the hadrosaurs. But individual locations, such as Hell Creek, seem to be diverse up to the extinction. Could there have been new challenges that the dinosaurs could adapt to? A lot of these studies are very reliant on how diversity is classified and can be affected by inherent biases in the fossil record. So that's the caveat to keep in mind when you're looking at this sort of thing. But it's very clear that even if they were already on their way out, they were killed off by this meteorite. It was their last, the bullet that finally killed them off. Except for the birds. So, lastly, how do we know that it was in June? We have two culprits right here. So firstly, we see here the sturgeon. Fossils of these fish have been found in deposits of the immediate aftermath of the extinction that shows that their last growth in increment was on the transition between spring and summer. Secondly, there are water lilies in lake deposits at the Teapot Dome site in Wyoming that appear to have been frozen on their growth trajectory towards summer leaves, flowers, and fruit. These both show an impact of around early summer. So, probably about June. So, that's the end of the lecture. And as always, thanks for listening.